So on the last page, we looked at nuclear fission. Fission is F-I-S-S-I-O-N, and that is splitting of a nucleus. Nuclear fusion, if you look at the root word there, that root word is F-U-S, fuse. So fuse means join together. So fusion, so fuse again means join together. So fusion reactions are joining together. Notice they're very small nuclei. So it's got like one proton and one neutron in there. Two very small nuclei. On fission, it was a mass number of 235. Here the mass number is 2. So very small nuclei joined together to make another small nuclei, but this produces a lot of energy. So for balancing nuclear reactions, again, we would look here and we would have big 4 times this 1 here, and so that's a total of 4 for the mass number. And so if I balance my nuclear reactions on top, 4 equals something, I don't know, plus 2 times 0, which is 0. So this top number here must be 4. For the bottom here, I'm going to have 4 times 1, so 4 equals something, that's my question mark, my unknown, plus 2 times 1, which is 2. So this bottom number here must be a 2. And so what does that mean? This right here, 4,2He, is how I would balance this nuclear reaction, by balancing my mass number and then balancing my atomic number. Repeating that process on the last problem here, I'm going to have 2 plus 2 is 4 equals an unknown. Well, again, you'll notice these are easier to do than the fission reactions because the numbers are a little bit simpler. So my top number must be 4. And on the bottom, balancing my atomic numbers, I have 1 plus 1 equals 2. And so that's, again, how I'm going to balance it. You'll notice most of these fusion reactions involve hydrogen and helium. And where does the fusion reaction occur? Okay, you've maybe heard about where does it mainly occur? It occurs on the sun. This is the process that is powering the sun. And again, always, this is not a reaction involving the electrons. This is a reaction involving the nucleus. So nuclear energy involves the nucleus. Okay, so they occur in the nucleus and they occur on the sun. Where is the other? Is there any place on Earth that this happens? Well, there's 2 thoughts on this. One, if it happens in what are called hydrogen bombs. So if you look at nuclear reactions, or nuclear weapons, I should say, old nuclear weapons were used fission. Newer, not that new anymore, but more modern nuclear weapons use a fission reaction to start off a fusion reaction, which is what makes them so much more powerful. And they call them H-bombs because you can see they involve hydrogen. So this is a fusion reaction. And they occur, so where do these occur? Again, in the nucleus, but this is the reaction that occurs on the sun or in hydrogen bombs. If you can figure out how to contain and control nuclear fusion, this would be an amazing thing you could figure out. You would do a lot of good for the world, because this would be a great way to generate energy and generate electricity, because one big advantage of fusion is there's not the nuclear waste associated with nuclear fission. So you can ask more questions about that, but that's just kind of the basics of, very, very basics of nuclear fusion. Lastly, on this page, again, how many protons, neutrons, and what is the mass number of here, uranium-235 and uranium-238. The uranium-235, 235 is the mass number. The mass number is made up of the protons plus the neutrons. And so when I look at the protons plus the neutrons, how do I know which one it's going to be? If you look at the periodic table, you'll find that the atomic number of uranium, the U, is 92. That's never going to change. So when I use my periodic table, again, they would give you this reference if they asked for this on the AP test, or they would tell you the number of protons is 92. And so then I can solve that, or plug that into my equation, and then solve for my neutrons, and my number of neutrons would be 143. In uranium-238, it's going to be the exact same process, but rather than a mass number of 235, it's 238 is going to equal protons plus neutrons. The protons never changes, so the protons is 92. And as a result, then, I solve this, and my number of neutrons is going to be 135. nope, I did that wrong. I'm sorry. It's going to be 146. 146 neutrons. And so here, what is the difference between uranium-238 and uranium-235? The difference is 3 neutrons. Uranium-238 has 3 more neutrons than uranium-235. We might not think that that's a big deal, but that really makes a huge difference. It's actually very different in half-life. And uranium-235 is what is used in nuclear power plants versus uranium-238 is actually the most abundant form of uranium. And that's what they have to mine a lot of. Over 90% of all uranium is this U-238. And this U-238 has a very, very, very long half-life. And that's why we can use it, or we can't use it for nuclear power plants. Again, we can get into more of those details, but essentially, big idea from this is understanding that mass number is protons plus neutrons. The protons never changes, so the number of protons is fixed, and that determines what the element is. And then from the mass number, you can determine the number of neutrons. And so isotopes have, and again, this word we've seen before, but isotopes have the same number of protons, so same number of protons, but different number of neutrons. Different number of neutrons. Hashtag is another way of saying number. I hope that gives you a basic intro of fusion reactions and mass number. Thanks.